let's see, exam on Monday. And here's what you can expect. I'll have you download a data set that has a numeric response, just a univariate numeric response, and a handful, like 2 or 3 or 4 predictor variables, numeric. So this is the numeric response. And these are a handful of numeric predictors. And I will ask you to use linear regression. Did you have a question? No? Okay. I'll ask you to use linear regression to model y as a function of x. So this will be the form of your model. yi is beta 0 plus beta 1 x1i dot 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 plus random error. And I'm going to ask you to do a simple model selection exercise. So selection, by that I mean if we're considering linear regression models of this form, what if we picked a different collection of, or a subset of the predictor variables? We could consider transformations of the predictor variables. We could consider lasso. The selection aspect is I've named a class of models, but now I want to tune to pick the best one. So for selection, I'm going to ask you to use leave one out cross-validation to estimate the MSE for 2 or 3 models, probably 3. Model 1, which will be of the form, let's say x1 plus x2, and model 2 of the form x1 plus x2 plus x3, and then another one that is another combination of the predictor variables. So we could just say x1, x2, x3, x4. But my intention is just to say we're going to consider 3 flavors of our model. We're setting up an exercise for tuning our predictive model. Remember that any predictive model can be tuned, and we've used a few different tuning parameters depending on the model we've used. With logistic regression, we tuned the probability of a particular class. With lasso, we tune the shrinkage parameter. In LDA and QDA, we also can tune the posterior probability of a particular class. So here we're just going to tune with respect to which of the predictor variables we use. And I want you to just illustrate to me that you know how to fit a handful of models using the variables that we have. So use leave one out cross-validation to estimate the MSE, and I'll ask you to comment based on what you saw, which is the model you would recommend. And that's asking which model has the lowest estimated MSE. And then, like you've done in the practice assignment, for the selected model, whichever of those handful that had the lowest estimated MSE, use Bootstrap to estimate the SD of the MSE estimate. So very much like what's in that practice problem. And let me just comment on something here to clarify. For cross-validation, that second part of the, or that initial part of the problem, that using cross-validation, remember that, well, let me say it this way. For the bootstrap step, I intend for you to do this using all the training data. So in particular, I'm not asking you to do any nested loops, although that would be arguably better to nest the bootstrap loop inside of the cross-validation routine. We know, so by doing it this way that I'm describing, you apply cross-validation to pick the model that you want, and then here's the model that we picked, model 2, say, and now I want an estimate of the MSE, or the standard deviation of the MSE for that model. So to do it, I'm going to take all the training data and fit that model inside a bootstrap loop. Sample with replacement, fit the model to all the sampled data, sample with replacement, and keep going. But we're sampling with replacement from all the training data. That might sound funny with respect to some things we've seen earlier in the class, that using just the training data to estimate accuracy results in an optimistic accuracy estimate. We'll always appear to have greater accuracy on the training data than on a test data set. So doing the estimation of the SD with the bootstrap this way, I expect that the estimated MSEs that we compute inside the bootstrap loop will be optimistic. But I'm counting on the variability of those estimates to not be so different, whether we look at a training or a testing set. So if you're in the real world and have your name attached to a real world data analysis project, and you're going to use cross-validation to tune and bootstrap to get an SD estimate, it could be marginally better to work harder to encode everything in a double nested loop. But I'm not asking you to do that because I don't think it makes that big of a difference in this case. But that's the exam. So it shouldn't take, given that you've done this and you have example code for doing this, I don't think the actual coding should take very long. This was designed in order to make it as reasonable to complete in the allotted time, 50 minutes, which is not very long. So I recommend get yourself an R script that illustrates doing this, either with an example we've seen or another a generic code maybe. Bring that in and you should be able to replace the data set name and the variable names and do some minor tweaking to make it run for the exam.
Professor,
Mm-hmm.
models are going to be given or
Models will be given, yeah. Here's the response, here's the predictors. We're going to consider a linear regression model, and I want you to try this one and that one and this one. I won't require any transformation of the data. It'll just be a model in terms of the actual variable names that are provided. Okay. Yes?
Can you comment on the degree of freedom in natural science? How
Sure.
you can change the random variable?
Okay. Question was about the degrees of freedom in a spline. That degrees of freedom for a spline, as we've said, has to do with how curvy the spline is allowed to be. The general idea of a spline is to create bins with what are called knots. So these are just locations of bin intervals. And within each bin, to fit a smooth curve subject to restrictions such that the curves in the different bins connect and that they're continuous where they connect. But beyond that, we could have relatively smooth curves and we could have much curvier curves. And that's a function of how many degrees of freedom do we allow the curve. The idea of degrees of freedom for this curve, think of it like this curve is a model-based representation of my data here. And I can have a more complex or less complex model. I could, for example, use more or less parameters for defining this curve. So degrees of freedom is like how deeply to dig in the data to create parameters that create a curvy curve. So degrees of freedom in a spline context, it's about how curvy. How do you know how many is appropriate? Is that what you were going to ask? Yeah, okay. So how do you know how many are appropriate? If we had this data set, this scatter plot, both curves do what was asked of them. They both kind of show the pattern, but obviously one is much smoother than the other. So if the goal is prediction, which is what we've been talking about, then we can quantify accuracy of the overall curve. So a natural measure to consider is a mean squared error. We've seen before that mean squared error is equal to bias squared plus the variance of the model. Curvier models will tend to have less bias but be higher in variance. So it's not necessarily clear whether you want the smooth one or the curvy one, or the really curvy one. That's the type of thing that you would tune. If this was my predictive model, response is a curvy function of predictor variables, and I'm going to use splines. A tuning parameter would be how curvy should I let the splines be. So if you use cross-validation or a validation set to tune the model, you'll essentially be estimating this and picking the degrees of freedom that optimize that. That will automatically be making the decision for you about how much bias, how much variance is optimal. So long story short, if you're using a spline model for prediction, do cross-validation to tune how curvy the curves are. Is that okay? Okay. Yeah.
So using cross-validation both for the nodes and the degree of freedom in this process?
So in this context, use cross-validation for the non-standard degrees of freedom. Is that what you said?
Where to place the bins with the nodes?
Oh, yeah. So that's another thing that could be considered. Question was, what about the knots? That's another kind of parameter of my spline. That could also be done with a tuning process. So you can tune as many things as you want. You may just have to have a really complicated loop or multiple loops, which can be time consuming. I think in practice, most people don't think too hardly about the knots. I think there are some good rules of thumb that seem to work well in most cases. So when I've used splines, I just used the default, but that's not to say that's the best answer in every case. You could certainly tune the model with respect to how many knots and where are they, and how many degrees of freedom of the curve. If you look at the spline function in R, the help file, it shows you some options for naming the knots, and it tells you what it does by default. So I'll look at the help file for NS. There is a knots argument. These are the breakpoints that define the spline. I'm not sure what they mean by no knots. That sounds like it's going to result in just a linear regression model. Sounds like if you say null for the knots, it's going to, oh, okay, so there's a trade-off, or there's a joint kind of relationship between the degrees of freedom and the knots. So if I specify a certain number of degrees of freedom, it's going to pick a corresponding number of knots. So if I specify this, this is automatically being specified. But that does not mean that we can't tune this as well. So it's not really clear to me from, typical values are the mean or median for one knot quantiles. So typical values, default choices of knots would be quantiles. If you have x on the horizontal axis, that is the predictor variable. Where to put knots, you pick how many knots, and it will put them at an appropriate quantiles. If it's 3 knots, then at 33rd percentile, 66, and so on. But it is something that can be tuned. With the time we have left, I wanted to lecture a little bit on tree-based methods. This won't be on the exam, but I want you to have at least seen them. There's another chapter in this book that I don't think we're going to have time to get to on what's called support vector machines. And so in the big picture of this book and predictive modeling, we've talked about simpler versus more complex models. LDA and logistic regression, those are really simple models. So is linear regression. Things like lasso, tree-based methods, or at least some of them, and support vector machines, and also neural networks are examples of really complex predictive models. In real-world applications where there's a ton of data, say, and we just need as accurate a prediction as is humanly possible, often the really sophisticated ones win. Support vector machines tend to be very accurate, so do neural networks. Random forests are up there as well. There is some challenge with applying the more sophisticated models in practice because tuning the model requires some level of expertise. It's a little more complicated than just doing the tuning that we've done with our simple models. So if you're finding yourself doing predictive modeling for a living, I recommend do some more reading on SVM and neural networks. And I think you'd need to do a little more study on your own to be able to be proficient with them. But they do work really well in complex cases. So let's talk about tree-based methods. I said last time these are totally different from what we've done so far. They're not a regression model. They're not a Bayesian posterior probability calculation. They're different. The idea is to take the predictor variable and break it into categories. So suppose we have a numeric response and one numeric predictor variable. And I want to predict the value of y in terms of x. A strategy we could try is there a threshold above which, when x is above that threshold, y tends to take a particular value? And if x is below that threshold, it takes a different value. So could we take numeric y and numeric x and say if x is bigger than some threshold, then I'll predict y1. If x is less than or equal to that threshold, I'll predict y2. Something like Hall of Fame, that's not a numeric response, but still in the Hall of Fame context, we could take one of those numeric predictor variables like batting average and try to find a threshold where most people who are in the Hall of Fame had a high batting average. So most people who had a batting average of this amount or bigger are in the Hall of Fame. That'd be one really simple way to make a prediction. Just pick a number, and if X is bigger than it, predict one thing. And then where it becomes more pragmatic, I guess, is that we can say, well, maybe I don't want to make a prediction of the same thing for every individual with X bigger than C. Maybe I want to split again. So if X is bigger than C, then I'm going to ask a different question. Now is X, let's say, bigger than C but less than D? Or is X bigger than D, less than E? What I'm trying to say is we initially just split based on that one threshold, based on X. I could split just that one time and make two possible predictions. That's probably not going to be very capable of accurate predictions in a complex process. So we probably want to do additional subsplitting. If X is bigger than C, okay, you're in a certain camp, but now I'm going to get more specific by continuing to split on X. Building a tree, a predictive tree, is doing this. And you can kind of hopefully imagine what the process would be for building this. The first step, the very first thing we did in building this tree was look for a threshold C that is the best single threshold for splitting the data into two predictions. So you could consider every possible C and quantify the resulting accuracy that you get by making a split that way. That gives you the initial splitting threshold. Then you can continue to do those types of considerations further down the tree branches. I won't show you the actual mathematics of the algorithm. It's mostly a computational algorithm. There's not really any fancy math behind a tree. So an algorithm will take our training data and make one of these for us. Then a prediction, if we had a new individual with a particular X value of X star, our prediction would be to take that and put it in the appropriate place in the tree. And whatever is below that node is our prediction. So just to emphasize, if we had a numeric Y here, our prediction based on this model only has 6 possible values that it would return. A tree will necessarily result in kind of grainy predictions. It's not real numbers that are returned. Well, it can't be real numbers, but it's a finite set of defined numbers that are returned. Trees. Trees are, they have some nice features to them. First and foremost, I think that they are highly interpretable. If my goal is to predict salary of a baseball player, and I can make this picture, then you could just print that out and you know the prediction for any player. It's very simple. Very simple to implement and simple to explain. But tree-based methods that are just like I drew on the whiteboard, very simple trees tend to not be as accurate as more sophisticated algorithms. So on the one hand, trees are nice and simple and interpretable, but on the other hand, they're not typically competitive with other methods. So what we end up doing is a fancy version of trees. We don't typically in practice take your training data and produce one tree. There are some sophisticated add-ons that substantially improve the accuracy of a tree-based model. So I will say a little bit about these things called bagging and boosting. Random forests are the result of tree-based methods where you did bagging and or boosting. But the big idea is that while a tree on its own is not generally very accurate, if you employ some resampling techniques, is what bagging and boosting are. If you apply some resampling techniques, you get a more complex model, not as easy to interpret, but much more accurate in general. Uh-huh.
Is there a difference between the tree diagram you drew and the dendrograms we did?
Yeah, so what's the relationship, if any, between clustering dendrogram and this picture? Yeah.
Do they do the same thing?
It's not the same thing. They're using different approaches. The clustering dendrogram is all about distances. And clustering is generally about the x's, or just no response variable. Yeah. When we cluster, we don't usually have a response variable that we're doing it with respect to. This predictive modeling tree is picking the bin or the groupings with respect to y. So they are different. Good question, though. Decision trees, they apply regardless of whether the response is numeric or categorical, so that's nice. Yes, sir?
And before us putting if we run the clustering instead of we just should we get the same result instead of us telling it beforehand?
So if you did clustering with these data, the way it would work is you'd have to identify, here's my matrix of numbers that I want to do clustering on. And that is asking, find the groupings of the columns of that data set that reflect structure in the data. So you would take like the matrix of x's, or you could put y in there as a column, and then you have the x's and the y. But what clustering is going to do is look for which of the variables group together, or which of the individuals group together. It's not anything with respect to x related to y, though. Clustering is just take your numeric variables and group them, or group the individuals in terms of them. This is different because the exercise is more, what can I do to x to maximize my accuracy in predicting y? It's a totally different task. So I would not expect, like if you did clustering of x, it doesn't make sense. You wouldn't get this if you did clustering of x and y. So if you did clustering of x, you would get groupings of the x variables, but they wouldn't have been constructed with predicting y in mind. So I would expect generally they would give you totally different pictures because they're trying to do different things. So trees work for both numeric and categorical response, what the book calls regression for a numeric response and classification for a categorical response. If your response is numeric, though, that point that I made about having kind of coarse, granular predictions comes into play because a tree can't give you, or at least this tree cannot give you like uniformly or normally distributed numbers. It's going to give you a handful of set numbers. Let's talk through this example that they have. It is baseball again, and it's salary. So we have two predictor variables. How many years has a baseball player been in the league is on the horizontal axis. And then on the vertical axis, how many career, I guess, hits have they had? Or how many hits a year probably is what it is on average. So each player in our training data set is a dot. And then the color of the dot indicates salary. Low salaries are blue-green, high salaries are yellow and red. So this is just a numeric response variable, salary, and two numeric predictor variables, hits and years. Here's how a decision tree would be constructed, at least the initial portion. The first thing that we would do, if we considered both of those variables, years and hits, and tried to find the single threshold for one of them that results in the best accuracy for prediction, it's going to be terrible prediction at this stage, because I'm either going to predict 5.11 or something else based on how many years they've been in the league. So this is not accurate at this point. But among all single thresholds, we could pick the one that does the best. So it turns out with these data, that threshold, the optimal initial threshold, is 4.5 years. If a player has played less than 4.5 years, with a tree grown to just this complexity, my prediction would be 5.11. If they had at least 4.5 years, then we picked a second consideration, a second split, based on the hits variable. So you've been in the league for a while. What does your average hits per year look like? Is it low or is it high? And here again, we picked the best single threshold that we could find. So that's the beginning of the tree. Let me go down here and show you. Oh, they don't have that picture. That's the beginning of a tree. We could grow a tree to further and further down. And you can imagine if you grow a tree far enough, you'll perfectly interpolate your training data. Just like with fitting a spline, you can perfectly match your training data. With a tree, if you keep splitting and splitting and splitting, ultimately you'll get the exact right prediction for every training individual. So in terms of tuning a tree, one of the big considerations is how deep to grow the tree. This is probably not accurate enough because it only gives 3 possible predictions. We could grow it all the way to its final complexity where it interpolates the data. That has 0 training error, but we know that probably will have poor generalizable error. So tuning the model can be, how deep should we go? Should we allow for 3 predictions, or should we grow it down to 20, or how far? And again, that's something we can use cross-validation or a train test split for. This just describes the tree. I already talked through it. And then this is an interesting picture. It illustrates in a scatter plot view what the tree did. So notice here's the same scatter plot that we saw earlier. It doesn't have the color coding anymore. And the breakdown of our tree, this tree that results in 3 possible predictions, you can visualize it as breaking the training space, predictor variable space, into 3 regions. If you're in region 1, we make that prediction. Region 1 corresponds to years less than 4.5. For players who have years bigger than 4.5, we ask a second question, and that is hits bigger than 117.5? So we wind up with 3 regions, R1, R2, R3, and predictions. You can either go through the tree step by step to decide where the prediction is, or you could look at a breakdown of a scatter plot like this and say, my particular player has years this, hits that. Which region is he in? That's your prediction. We don't need to know this language, I don't think, so I'm going to skip that. I'm going to skip that too. I want to get to random forests. Here is a formula for, well, this is just the residual sum of squares, like a mean squared error, except it's not a mean. It's just a sum of square deviations. And they're just saying this is the objective function that is used for making the splits. Step 1, let's pick one threshold for this predictor variable, and we'll try a bunch of different thresholds, and we'll pick the one that gives the lowest RSS. So this is used throughout the tree building process. Let me comment on this. If the goal is just very simply put to build the best tree, then that's not very well defined because that is computationally infeasible. Every initial split you pick determines what happens below it. So suppose you pick the best split in step 1, and then you keep going. Who's to say that a different split at step 1 wouldn't, in combination with the other steps that would follow it, result in a better accuracy overall? So what I mean to say is there's too many possible trees to consider to search for the best one in an exhaustive way. Often what people do with computational algorithms in cases like that is a greedy algorithm or greedy approximation. We've talked about something similar to this when we've talked about feature selection. Suppose we have a bunch of predictor variables, thousands of them, and we want to ask, can I find a subset of them that is sufficiently accurate? We could consider subsets of different sizes. Let's try taking the top 10, let's try taking the top 20, ... up to thousands. And for each one, estimate the accuracy. We used a greedy algorithm when we did that because otherwise, finding the best subset of size 100 from thousands is computationally infeasible. You have to go through, theoretically, every single possible collection of 100 to find the best subset of 100. So anyway, greedy algorithms often show up when we have an ideal quantity in mind that we would like to do, but computationally it's not feasible. Greedy just means you make the best initial move, and then you look at the next step and make the best move at that step and keep going, as opposed to trying to consider the whole thing simultaneously. Okay, we're running out of time. Pruning a tree is the idea of tuning the tree-based model. If you ask for a tree, R will fit the full tree. It will go all the way down to the point where you interpolate your data. That's not necessarily the tree you want to use, though, because it may overfit your training data. So the process of tuning the tree is, as I said earlier, deciding how far down the tree to go. So that's called pruning the tree. You can grow it all the way down to interpolation, and you can consider chopping back up How far up do you need to go to get the best overall accuracy? Cross-validation and mean squared error or the related residual sum of squares can be used. You would use a function in R to implement this. Here is a further grown tree for the baseball salary data. Hard to see, but this initial split is the same one we saw earlier, years less than 4.5. And then in the tree that we saw earlier, we only had this second split. If years is bigger than or equal to 4.5, then ask is hits less than 117.5. So this is the result of letting the tree go further. The next split that was considered was on the left side of the tree, and that is RBI less than 60.5. So split, split, lots of these little splits, and so you have many more possible predictions than we had in the original tree. I think what the authors say in this part of the slides is that this is the tree that was selected based on cross-validation. Pruning the tree from perfect prediction, interpolation, up to the point that best results in a balance of accuracy gets you here. This is a picture that's similar to ones we've seen where we consider tuning parameter and an error base or an accuracy estimate. Mean squared error versus tree size. So this is for pruning or tuning the tree. How many predictions should you end up making? You can quantify that as the tree size. How many nodes, how many endpoints are there total in your model? More tree or a bigger tree size means a more complex model. So we can use cross-validation or a train test split and try to find where's the best trade-off. Where is the tree size that's as small as possible while getting us as high of accuracy as possible. So for this example, you could argue strongly that a tree of size 3 is our best choice because tree of size 1, these error rates are relatively high. I can decrease substantially the error by growing it to 2, size of 2, and then I can decrease the accuracy reasonably by going from 2 to 3. From there on out, though, the accuracy looks relatively flat, so there's no need to grow to greater depth. You would prefer a smaller tree to a larger one, just because there's better chance of being able to interpret and explain it than if it has lots and lots of nodes. Let me skip forward a little bit. This section of the notes changes gears from the numeric response to the categorical response. So we can do classification with these trees as well. If your hits is below this threshold, I'll predict you're not in the Hall of Fame. If it's above that threshold, I'll predict you are in the Hall of Fame. And then you could keep growing it, but you're always making predictions of a categorical thing. It's the same basic idea. The details of the algorithm is a little bit different, but it's the same idea. Okay, I'll have to pick this back up on Wednesday. Do we have class Wednesday? I think we do, yeah, on Wednesday. But ways of greatly improving the accuracy of a tree-based model is bagging and what's called boosting. Bagging is an implementation of the bootstrap. So the concept is not complicated, but the idea for both of these is that instead of growing a single tree and using that one tree as your prediction, your predictions are based on like a forest of trees, a collection of trees. You fit a tree, and then you could sample with replacement from your training data and fit another tree, and do it again, and do it again, and do it again. It turns out that if you have these bootstrapped versions of your trees, and you make predictions for each of them and average the results, you can get substantially better accuracy than just picking any one tree on its own. Typically in practice, when people use tree-based methods, they're using one of these bagged or boosted trees. And random forest is one specific example. Just for reference, I'll show you this on Wednesday, but in the Hall of Fame data, our script, I have an example of using random forest. So I'll show you this next time. But there's a built-in package for random forest. There's a separate package for trees. So random forest is kind of its own specialized thing. But it's easy to use, usual model-based syntax, and then you can use a predict function. Okay. All right, so come ready to take your exam on Monday. I'll be here a few minutes early. If you want to come a few minutes early, that's fine, but I can't open it up all that much early. Okay. All right, have a good weekend.